So here is a 3D example where we have 3 bars in space. I have 1, I have a 2, and I have a 3. They are pinned at 3, 2, and 4. And at 1, they are supported on a wall that is in the XZ plane. So I hope you can all visualize this 3D. So we have X, Y. So this XY plane. The vertical is the YZ. And the other vertical is the XZ. Most of us are used to have the XY as a vertical plane. So this here is a bit different. But it shouldn't really affect anything as long as we follow the directions. Now, the first thing I want to give here are the ordinates of these points. So I have here point 1. As you can see, point 1 is on the x-axis, So its y ordinate is a 0, the z ordinate is a 0. And along the x, it is 72, 0, and 0. Our second point is on the y-axis and is sitting at a distance of 36. And in the x direction, it is at a 0. So 0, 36, and 0. Point 3 is sitting in the YZ plane. YZ plane. So x is a 0. And in the y direction, it is up 36. I'm sorry, that's the y direction. So that would be this distance here, 36. And then in the vertical direction, the z, it is at 72. So you can see this distance is almost the same as this. And point 4 has is along the z-axis. So it has a 0x, a 0y, and in the z direction, it is at minus 48. Bar 1 has an area of 0.302 square inch, and bar 2 has an area of 0.729 square inch. And bar 3 has an area of 0.187 square inch. So these are all the areas. And the 3 bars are made of the same material, and they have a modulus of elasticity, E, of 1.2 times 10 to the power 6 psi. Point 1 has a force applied on it of 1,000 pounds. We want to find the axial stress in bar 1, in bar 2, and in bar 3. So we learned how to compute stresses for bar elements in plane. And likewise, we're going to do the same for 3D. So let me explain that first. So we know that our goal is to find the global displacements, and then we can use them to find stresses. So computation of the axial stress sigma in a bar in 3D.
Is node 1 fixed?
node 1 is restrained from moving into the XZ plane, right? So what would that mean? It can slide in the X direction and in the Z direction, but it cannot move in the perpendicular direction, which is the Y direction. So it's like a roller in 3D. Make sense?
Yes.
Okay. So in 2D, we were able to write the expression that sigma is equal to E over L times -1 and 1 multiplied by T multiplied by D. And we call that C prime times D. And C prime was defined by this portion here. And when we solved for this, we said this is equal to E over L multiplied by minus C minus S, C and S multiplied by D, which is in 2D was given by U1, V1, U2, and V2. And just to remind you, when we were working in plane, if I was working in the XY plane, the bar that we're referring to here in the X prime had an angle theta X. And this here is minus cosine theta X minus sine theta X and so on. If I call this angle theta Y, I can replace the sine by cosine theta Y. Would be the same thing, correct? So in 3D, it's going to be similar. We're going to get sigma is equal to, I get this E over L, and then I have minus Cx cosine theta X. For minus sine theta X, I'm going to use cosine theta Y. So I have a minus cosine Y, and I'm going to continue for the third direction minus CZ, and then plus Cx plus Cy plus Cz multiplied by U1, V1, W1, U2, V2, and W2. So this is the expression we're going to use to find the stresses in the bar. Of course, here 1 is my start node, and 2 is my end node. So here that would be 1 and 2. Okay. So let's go back to our example and apply these. So our goal, in order to find the stresses in this problem, would be to find all the displacements. And as you can all see, we're going to take advantage of all the boundary conditions. So for this problem, though we have 4 nodes, right? 1, 2, 3, and 4. Each node has 3 degrees of freedom. So I should have a total of 12 degrees of freedom. How many of them are really free? Only 2, right? So my goal here would be to focus on these two because I can eliminate all the rows and columns corresponding to the boundary conditions. Does anyone still need this? So in order to get to the modified stiffness equations, we first need to write the element stiffness matrices. Which is, as we learned, I'm going to have K equals to lambda, right, minus lambda, and lambda, where lambda is equal to Cx squared, Cx Cy, Cx Cz, Cy Cx Cy squared, Cy Cz, Cz Cx, Cz Cy, and Cz squared. So clearly we need to find the cosines for each of these elements. So I'm going to start here with element 1. And we're going to repeat for all the elements. In order for me to find the cosine angles, I'm going to need to find the length first. So if I look at the length of 1, so L1 is equal to the square root of x. 1 extends between node 1 and node 2. So I have x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. This is equal to the square root of x2, I have a 0, minus x1 is a 72 squared, plus y2 is a 36, minus 0 squared, plus z2 is a 0 minus 0 squared. When I do the numbers, I get here 80.5 inches. Next, we want to find Cx, Cy, and Cz. Okay. So Cx would be equal to x2 minus x1 over L, which is equal to 0 minus 72 divided by 80.5. This is equal to minus 0.89. Cy would be y2 minus y1 over L, which is equal to 36 minus 0 over 80.5. I get a 0.45. Cz is equal to z2 minus z1 over L, and all these L's are L1s, of course. I get here a 0 minus 0 divided by 80.5, so we get a 0. So we have all the cosine angles for element 1. I'm going to try to keep the diagram here as I work on the other elements so you can see it. For element 2, we are going to start by finding L2 equals to the square root. Look here at 2. It extends between 1 and 3, goes from 1 to 3. And again, the local directions are important. I think I should have shown these first. So we have decided to make 1. This would be for element 1. This would be x1 prime. For element 2, going from 1 to 3, this is x2 prime. And for element 3, that would be x3 prime. So it is really important to mark these. So when we're finding the cosine angles, we're finding them in the right direction. All right. So for element 2, I'm looking at element 2. I have a 0 minus 72 squared plus 36 minus 0 squared plus 72 minus 0 squared. And I get here 108.0 inches. Next, we're going to look at CX, CY, and CZ. So CX would be 0 minus 72 divided by 108. I get a minus 0.667. For CY, I get a 36 minus 0 over 108, and I get here 0.333. Of course, I would recommend using at least 5 significant digits, but let's focus here on the process. CZ would be this 72 minus 0 divided by 108, and I get 0.667. Next, we go to element 3. I have an L3 that is equal to the square root of. So element 3 extends from 1 to 4. So I would be looking at a 0 minus 72 squared plus 0 minus 0 squared plus minus 48 minus 0 squared. And I get here 86.533 inches. Next, we look at CX, CY, and CZ. And you can see here where a computer program would be very handy, right? With the repetitive process. All right, so CX would be 0 minus 72 divided by 86.533. I get here a 0.83205. CY, I have here 0 minus 0 divided by 86.533 is equal to 0. And finally, a minus 48 minus 0 divided by 86.533, we get here a minus 0.5547. So even though you can program something like this in MATLAB, I encourage you for the first problems to work it by hand so you can get the concepts and the process, all right? Make it visual in any ways, right? Even sometimes we can use something like Excel spreadsheets so we can see everything. All right, we are ready then to write the lambdas for each of these elements, right? So in order to write the element stiffness matrices. So I'm going to come here for still working on element stiffness matrices. So back to element 1. I can write lambda 1 as equal to, and we defined lambda. So I'm just going to write the numerical values given that we have Cx, Cy, and Cz. So first I have minus 0.89 squared. That would be a 0.79. Again, with approximation here, using only 2 significant digits. Minus 0.4 for Cx, Cy. And Cx, Cz would be a 0. Cy squared, that's 0.45 squared. I'm going to get like a 0.2. Cz squared is a 0. Cy, Cz would be a 0. It is symmetric, so I have here a minus 0.4, a 0, and a 0. So that would be lambda 1. So what would K1 look like? And I did a mistake here. I did not include EA over L. I have to write this before the lambda. So please correct that. So for element 1, the area is 0.302 square inch, and E is 1.2 times 10 to the power 6. And L1 was 80.5. And we are going to have here a 6 by 6 matrix. That simply, I'm going to put lambda 1 minus lambda 1 minus lambda 1 and lambda 1. But more importantly, I would like to mark the rows and the columns to their corresponding degrees of freedom. So for element 1, extends from 1 to 2. I'm going to have here, or see, a U1, V1, and W1. And then it goes to node 2. So I'm going to see a U2, V2, and W2. Likewise, I can label the columns. Why am I doing this? Because when I write my modified equations, I'm going to be mostly interested in which degrees of freedom? U1 and?
U1.
Okay, V1 is a 0, right? But W1 is free. So I'll be looking at so keep that in mind. And I'm going to be able to get these from here if I look at my first column, third column, right? So I will be looking at these entries here and the corresponding ones, right? So we're going to come back to these. But of course, I have to multiply it by EA over L. Okay, so we're going to continue to look for the other elements. So element 2 we are going to have this K2 that is equal to area 2 is 0.729 multiplied by E, which is 1.2 times 10 to the power 6, divided by the length of element 2, which we found to be 108. And this is going to be multiplied by, again, lambda 2 minus lambda 2 minus lambda 2 and lambda 2. So we need to define lambda 2. So lambda 2, again, we have the cosine squared. So minus 0.667 squared, I will get a 0.45. Cx, Cy, I get here a minus 0.22. Cx, Cz, I will get a minus 0.45. Oops. Let's keep this at 0.45. Then I have here a Cy squared. So I have for element 2, it's 0.33 squared. So I will get a 0.11. I have a Cy Cz 0.33 times 0.667. We're going to get a 0.22. And the Cz squared, I'm going to get 0.667 squared. I'm going to get a 0.45. And it is symmetric. If I want to reference degrees of freedom for element 2 extends from 1 to 3. So I'm going to have here U1, V1, W1, U3, V3, and W3. Okay. So again, the ones that I'm going to be interested in are going to be U1, W1, W1, U1, and W1, W1. And finally, element 3. We're going to have a K3 that is equal to the area 3 is 0.187 times E, which is 1.2 times 10 to the power 6, divided by the length of element 3, which is 86.533, multiplied by lambda 3 minus lambda 3 minus lambda 3 and lambda 3. Element 3 extends between 1 and 3. So I'm going to get U1, V1, W1. I'm sorry, that's 2. I'm looking at 3 here. Okay. So from 1 to 4, right? So I'm going to get here U4, V4, W4. Likewise, U1, V1, W1, U4, V4, and W4. Okay. So let's write lambda 3. So if I'm looking at element 3, Cx squared, 0.83 squared, I'll get here a 0.6923, 6923. And then I have Cxcy, that's a 0. Then I have Cxcz, 0.83 times minus 0.55. Yeah, minus 0.55. So that should be minus 0.4615. Then I have Cy squared, that's a 0. Cy, Cz is a 0. Then we have finally Cz squared, which is minus 0.554 squared. I get a 0.3077. It's symmetric, so I get here a 0. I have here a minus 0.4615, and I have here a 0. Again, we're interested in U1 and W1. So primarily, we're going to be looking at these, of course, multiplied by EA over L. So just to recap, we had 4 nodes times 3 degrees of freedom per node equal 12 degrees of freedom total. But we have less 10 degrees of freedom restraint. So I conclude here that we have 2 degrees of freedom that are free. And these are the ones we want to solve for. So I'm going to come up here with a modified K that is only a 2 by 2. And I do not want to bore you with the math, but basically we're going to be, in order to assemble this, we're going to be doing the summation of all the entries from the 3 elements. So these are going to be corresponding to U1, W1, U1, W1. So you should get 8997 minus 2447. And again, these numbers are approximate because we're not really putting all the significant digits. So if you do the numbers, it might be slightly off. Minus 2447 and 4423.
So, U1 is the sum of U1 in lambda 1, U1 in lambda 2, and U1 in lambda 3.
Oh, but remember to not the lambda, because I need to multiply by EA over L.
Yeah, okay, yeah.
Okay, don't forget that. Okay. So yes, I was marking the elements in the lambdas, but remember when we were writing K, we had the EA over L. Okay. Okay, so the modified equation, if I look at my structure here, what are the external forces corresponding to U1 and W1? So, yeah, 0 first, right? Because U is in the X direction. So I don't have any external forces applied in the X direction. So I'm going to start with a 0 followed by a minus 1,000. So when I'm writing my modified equation, I'm going to have a 0 and a minus 1,000. This is F is equal to this K, which is the 8997 minus 2447 minus 2447 and 4423 multiplied by U1 W1. This is my modified global stiffness equations after applying the boundary conditions. Okay. So when we solve, we'll get that U1 is equal to a minus 0.0720 inches, and W1 is equal to minus 0.2647 inches. And again, let's make sure our numbers make sense. When I apply 1,000 downwards, that's the Z direction. I expect the most significant displacement to be downward along the Z direction, which is the minus 0.2647. And along the X direction, as I pull, is going to move in the negative direction a fraction of the major displacement. So the numbers here do make sense. Next, we want to find the stresses or the stress rather in each element. So the stress equation, sigma, is equal to E over L multiplied by this row matrix of minus Cx minus Cy minus Cz plus Cx plus Cy plus Cz multiplied by U1 W1, or I can call it here I and J, UI VI WI, UJ VJ and WJ, where I is the start node and J is the end node.
Is there no K components?
Excuse me?
Is there no K components?
No K components?
Yes, not.
No, I am reusing I and J to refer to a start point and end point, not the unit vectors. Okay. So for element 1, sigma would be equal to E is 1.2 times 10 to the power 6. And L for element 1 was 80.5. Okay. Now, out of these displacements for element 1, everything is 0 except for UI and WI, which means I really care about the first and the third here, which is for element 1, I'm going to have a minus 0.89. I have a 0.45, and I need to change the sign. And I have a 0. Then we're going to have, again, these 0.8 minus 0.89, 0.45, and a 0, multiplied by U1 or UI here would be a minus 0.720. I have a 0, then I have a minus 0.2647. Then we have 0, 0, 0. This is sigma for element 1. When I do the math, I'll get that sigma for element 1 is equal to minus 945 psi. I trust you can repeat the same for element 2 and for element 3. So for element 2, when you do the numbers, you will get 1,440 psi. And for element 3, you're going to get a sigma 3 that is equal to, minus 2,850 psi. Let's look at these numbers as they relate to the 3 bars. I like to make sure that our numbers are making sense. So we expect, as we put a 1,000 here, that element 2 is going to be stretched. And indeed it is. We get a plus. And element 3 gets compressed. And element 2 also gets compressed, pushed towards the wall. Excuse me? Element 1, I'm sorry.